Hello and welcome to the first session of our application of CFD in Formula Student workshop series by SimScale and Formula Student Germany. Today we will start our journey through the world of computational fluid dynamics and aerodynamics and start with the fundamentals of aerodynamics. And I'm very happy that we have a very well-known guest speaker today, René Hilhorst. I will introduce him in detail later, who will take over for this part of the presentation. First of all, I would like to introduce myself. My name is Milad. I'm the product marketing manager here at SimScale, and as part of this role, I'm organizing now for the third time the annual Formula Student CFD workshop. Before I've joined SimScale, I've also worked in motorsports in the aerodynamics department as a CFD engineer, including F1 and World Rally Championship. And before we start and I introduce you to René, I would like to discuss the agenda of today's webinar as well as some organizational things. All right, first of all, we will start to talk about some organizational aspect, as I mentioned. Then I will quickly introduce you to SimScale, the cloud-based simulation platform, which we will use during this course to set up the simulation. And SimScale is free of cost for you, so you can create a free community account and run your own simulations, and we will also provide you with some tutorials. Then René will take over and talk about three fundamental, let's say, elements of race car aerodynamics, and this will include really the real physical basics as well as some advanced stuff which is really important for you and for the design of the wing of your cars. At the end we will have a Q&A session, and you can write all the time, you can write us questions. We have this question toolbox inside GoToWebinar, which is the application we're using to provide you with the live stream of the session. And just write your question. We will try to answer them live and on the fly or latest during the Q&A. Just based on my experience, there will be a lot of questions, and usually we don't have the time to answer all of them. So please try to write the question in a very short way so that we can discuss most of them. All right, let's discuss some details and some basic things and thoughts about this workshop series and the webinars. So the overall aim of this workshop series, and it consists actually out of your webinars, is to teach the really fundamentals of aerodynamics and CFD, which you need as a, let's say, Formula student or aerodynamics newbie to be able to leverage CFD simulations for the development of the aerodynamic package of your Formula Student car. For sure, this course will not replace to read some books where fundamentals are taught, and also we recommend to have at least some fundamental knowledge about aerodynamics and fluid dynamics. However, we will focus more on hands-on aspects. So we will talk about theory, but only as much as necessary, and really try to focus on what you need to know to be able to not only create simulations of your own race car design, but really to leverage CFD for your race car development, to develop a process how you use this data to improve your race car. And this workshop actually consists out of two parts. On the one hand, we have our live webinar sessions, and during those live webinar sessions, we will discuss about different, let's say, chapters of our journey. And for every webinar session, we will prepare a couple of specific questions. And at the end of the workshop, there will be the possibility to get certified, and we can provide you with a certification that you attended this course. For this, you have to answer these questions. But if you don't want to have the certificate, you can only use them for self-control, and we will publish the answers somehow later. And we also provide you with tutorials and a CAD model and ready-to-use simulation projects, which you can use to run your own simulations. And in contrast to the last years, there will not be any more simulation homework, and therefore actually you can really start to simulate with your own model, or you can try to modify them, but it's not mandatory anymore. And also from my experience from the last 2 years, it's really more important to understand what we discussed during the session. In the end of the day, just rerunning the simulation, it's quite easy with SimScale because you can just replace the geometry in the end of the day. But really to be able to create good CFD results and good simulation results, you need to at least understand what will be discussed on during the next 4 webinar sessions. Yes, in the case you have questions or you need support setting up your own simulation, please use our SimScale forum. There we will create a dedicated subcategory where we will answer all your questions. Please don't write somewhere else in the forum. If it's related to the workshop or the content of the workshop, write it there. And please note that for the tutorials, we do not provide like any technical support through phone or something like that. So really use the forum, but we'll promise you every question, every problem will be answered and solved. And yes, at least because some people already asked, there are no special software or hardware required to join this webinar series. As I mentioned, there's also no prior knowledge, but for sure, at least you need to know the fundamentals of engineering, of physics somehow to understand what we are talking about. But as long as I think most of you are students, we really try to start with the basics and the fundamentals. And let's now take a quick look at our course and the curriculum and what we will learn. So today is our first session, which will be held by René Hilhorst. René is, I will introduce him later, but René really is I would say, aerodynamics veteran with a lot of experience in different racing series, and he will explain you some of the fundamentals of aerodynamics you need to know, and then he will focus on wing theory and wing design and really teach you the fundamentals you need to know to get started. Next week, and this is very important, all the other sessions will take place on a Thursday. Next week, Thursday, the same time, I will take over and introduce you to the fundamentals of complete aerodynamics and CFD. And we will basically talk about two things. First of all, I will introduce you to CFD and how to use, based on a project we've prepared, how to create a CFD simulation of a Formula Student car. And then we will talk about how to model the most important, let's say, aspects or aerodynamic phenomena, which is the more correct modeling of the wall and of the wheels and the radiator flow. The week after, Torbjörn Larsson will join. Torbjörn is the former head of CFD at Sauber, BMW Sauber and Ferrari F1, and he will explain how to create their own development strategy and how to really get the most out of your CFD work. And he will share some nice post-processing techniques with you. And the last session will focus on best practice about the design process, and there Niklas Pfeiffer will join, who is as the actual head of aerodynamics at the e-motorsports team from Cologne, and he is actually joining for the second time, and he has a lot of experience with, let's say, both sides of the medal, how it is to start from zero as a new user, and today he, as I mentioned, is really experienced, and he will share some insights from this year's car with us, and we will talk about how to use the tutorial templates to set up your own simulation. Yes, finally, I think we discussed most of the questions. Maybe one important thing, yes, we will record all the webinar sessions and provide you with the recording by email, and with this email we'll also send you some other relevant resources and links, like for example to the forum category where you can find support, or we will provide you with links to the tutorials. So just wait for the email, which should be in your inbox until the end of the week. Yes, and finally, before I hand over to Renee, I would like to mention our SimScale academic program, and SimScale actually sponsors every team, every official Formula Student team with a SimScale sponsoring package, and this includes different benefits. First of all, you get one team account which gives you access to unlimited core hours and private projects. Unlimited core hours, with this term we mean we will renew your core hour usage whenever it's necessary. However, yeah, you like have a budget which can be renewed several times a year, and as long as you use it meaningful, we never had in the past any issue to provide the teams with enough core hours. And besides this, you will get first of all access to some exclusive tools. One of them is a post-processing script which we have developed, which will fully automatically post-process all your simulation results, and which is only available to SimScale sponsored teams. You will get invited to exclusive webinars and trainings, and you get premium SimScale support via the chat and email. And to become a SimScale sponsored team, it's actually quite easy. And don't worry, we will also send you all the information by email, but you actually need first of all to download this form, which is the application form for the academic program, at the same time a sponsoring agreement, and there you just need to fill it out with like the primary contact, the contact details of the university, and actually once this form is signed, you just need to send it to us by email. Just send it to academic@simscale.com, and we will just check if your official team. With official, we mean that you are like enrolled for the for a formal student competition, or that you were enrolled at least in the past, or try to register. And this process will maybe take up to 1 week, and then you will be provided with all the with the account upgrade and all the other information you need. Well, and now I would like to quickly introduce you to SimScale. So for the practical part of the sessions, we will not necessarily demonstrate a lot, but if you want to run the simulations on your own, you can use the SimScale platform. And SimScale is a web-based simulation platform, which means you don't need to install any software, and all the computational resources will be provided through the cloud. So it's really makes you independent from any computing resources or licenses. And SimScale has a lot of unique features, especially if you compare it with traditional on-premise software. And I don't want to talk too much about this because that's not why you've joined the webinar. But I think the most important thing for you as a team is that it will allow you to collaborate. You don't have any more the big hassle of managing the ton of simulation data. Everybody who should access it can access the data through the SimScale interface from wherever you want. You will get provided for free with the computational power. You don't need a license. It's secure, and you get free support through our team if you're a sponsored team. Since some people asked, it's not necessary, by the way, to attend the whole webinars to give the exam, but if you have questions and if you want to ask our guest speaker and experts from motorsports, then you should join for the webinar for sure. Yes, and now it's a big pleasure for me to hand over the stage to René Hilhorst. Yes, René is really a well-known expert in the world of motorsports, and yes, he worked for several years as the first head of aerodynamics at Toyota Motorsports, and was responsible for the very first the aerodynamics of the very first Toyota F1 car. Today, René is working as a consultant and the managing director of his own company, where he's helping leading racing teams in racing series like Formula 1 and World Endurance Championship to optimize the performance of their car. René, can you hear us?
Hello?
Hi René, perfect. Seems like everything is working. I will make you know the presenter, and yeah, then you can take over.
Okay, fine for me. Hello. So the presentation that I will do today is to introduce you to the fundamentals of aerodynamics that are useful for race car development. And the first part is speaking about under layer. That's a thin layer that's close to the wall due to the viscosity of the air. And to introduce boundary layer, I would first like to show you,
René,
let's say,
can you make it full screen?
The full screen.
Click on Lire. Sorry, I don't speak French, but on the right side upper corner there's this play button. It will make it full screen. Yeah, you were there. No. Left, a little bit left.
Lire, okay.
Perfect, thanks.
It's loading. Yes. So first to remind everybody about the main air properties that will be of interest for the development. So obviously density, the air density, and defined as the term rho. In most of the cases, we will consider this as being a constant, so we will consider the fluid as incompressible. It's, as I said, in most of the cases, because people will work in, for instance, Formula 3, where there'll be kind of some air restrictors for the engine, then the flow can get sonic, and the Mach number will increase close to Mach 1 and reach Mach 1 at the throat at maximum flow rate. But globally, for the rest of the external aerodynamics, we can consider the fluid as incompressible. And the two other main properties that we will speak about all during the presentations is pressure and viscosity. Pressure, we have to remember that it always acts normal to the wall, to where it applies to, and viscosity will always apply tangentially to the wall. For the viscosity, to illustrate it in a kind of easy way, it is showing the quet experience. If, for instance, you put in a cylinder, you fill it with a viscous fluid, let's say let's say oil, for instance, and you put another cylinder inside. When you start to rotate the internal cylinder, due to the viscous forces, you will see that if you don't hold the external cylinder, little by little, this cylinder will start to move. Or you would need to apply a torque to hold it fixed. That will depend on the speed of the rotation and the viscosity of the fluid. And to kind of illustrate in a different way this experience, the quet experience of this cylinder rotating inside a bath of viscous fluid, you could unfold as an image the cylinder. Then you would have one wall, for instance on the sketch, the bottom wall would be the fixed wall, and you have a top wall moving at a speed of velocity v. So it has a differential speed between the non-moving wall at the bottom and the upper wall moving at speed v, and so you create a gradient, and the condition of adherence at the wall imposes that on the bottom wall you get zero speed as contact condition, so the walls are moving, so the particles in contact will have the same speed as the wall, so speed 0, and the particles in contact with the wall moving at speed v will move at the same speed. And so you will have in between the speed that has to evolve then between 0 and v, and creating this velocity profile evolving from 0 to v. And we demonstrate that then there's a kind of forces acting on the wall, and the forces acting on the wall are directly related to the viscosity of the fluid by the factor mu. The surface, obviously, the bigger the wall, the bigger the forces will be in Newton. The speed, so actually the speed differential between the two moving walls, and the distance between the two moving walls. So this is the first introduction to viscosity, and as a reminder, the viscous forces are acting tangentially to the wall. So then a small introduction to the Navier-Stokes situations. Obviously, we're not going to spend time to re-put them in equation. It is those are the equations of conservation. If you apply the main equation is the momentum conservation equation. So that can be translated by if you have F equal m gamma, so m being the mass, gamma the acceleration, and F are the propulsion or resistive forces. This is then the equilibrium of this momentum equation. That for the air can be translated in inertia effects, the terms on the left-hand side in this formula. So inertia effects will be, if we now speak, we saw the air properties are mainly pressure and viscosity that will create forces. We can neglect all volumetric forces like the gravity. So it will be the pressure acting and the viscosity acting. And so those two forces will then, the force coming from the pressure and the force coming from the viscosity, will then create the variation of speed of the air around the body, and hence the forces that were acting on it. So this is the first thing really to remember, is the balance between inertia, pressure, and viscosity. As you see, in this formula appear two kind of numbers without dimensions. They are similitude parameters or analogy parameters. They are very important for knowing the importance of each effect. I will start with the bottom one, the Mach number. Mach number is the ratio of the speed of the perturbations compared to the speed of sound. So, or the speed of the body. If your car moves at a given speed, how fast does it move compared to the speed of sound? So obviously, when it's equal to the speed of sound, we're at Mach 1. So it would be the transition between subsonic flows and supersonic flows. When you're higher than 1, it's supersonic. When you're moving faster than the perturbations you are emitting, you're supersonic. But for us, in most of the cases, we said we will be in the subsonic flow, so the speeds will be lower, quite much lower than the speed of sound. And the big consequence of this is, in subsonic, it means everything influences everything. So to take the example of a racing car, not only the front wing will influence the cockpit, the side pod inlets, the diffuser, and the rear wing, but the rear wing and the diffuser will have an effect on the front wing. So this is because we are in subsonic flow. And then the very important other parameter that is of interest is the one that is a factor, as we saw, of the viscous term, is the Reynolds number, and the Reynolds number is the ratio of the inertial effects over the viscous effects. What does it mean? It means that when the Reynolds number is very high, it means the viscosity will have a little effect overall, although being still present. And if this Reynolds number goes down, then the viscous effects, little by little, will be predominant compared to the inertial effects of the air. How is the Reynolds number defined? It is the ratio of the density of the reference density multiplied by the reference speed by a reference length divided by the viscosity of the fluid. So what does it mean is the faster we go, so the bigger the speed is, the higher the Reynolds number, so the more important are the inertial effects. The density is important, so when we are at sea level, the density is higher than in the mountains, high speed, like circuits like Sao Paulo have low density, or Mexico have low density, so there the Reynolds number will be lower. The length is the size of the body, it's the reference length, so for the cars we will often take kind of the wheelbase, but if we study rear wings we will take the chord of the wings. So this is the dimension of the object, and mu will be the viscosity of the air for us, and we have cars running in the air. So this will be an important parameter to look after. The boundary layer will then appear to define it. We spoke about before about the quad analogy, where we replace the top wall, where initially we replace a cylinder by two different walls. But now if we replace, in our previous example, if I go up rapidly, of the top wall moving above a bottom wall that's not moving, we can consider that flow over a body will see something similar. It means there is a body represented here by a still wall, and we have air flowing on top of it. So when we are far away from the body, we can imagine that in this case, where we look at the relative motion of the air at a speed of v in function in relation to a body that is then, suppose here, stationary, so we have really the relative motion of air compared to the wall, then we can imagine that far away from the body we will unavoidably refine the speed of air undisturbed v. So when we are far from the disturbance of the body, the air will have the same properties as the uniform flow v. And we still have the condition of zero velocity at the wall, or let's say the same velocity as the wall has. So it means here, as the wall is stationary, we will have again speed zero at the wall. That means, again, we will have a gradient of speed, a variation of speed of the air between no speed at the wall until the external speed outside, or let's say far away enough from the body. And we can then define in this way the definition of the boundary layer. It tells actually the thickness at which we will refine the external speed of v. And to make it, obviously, when you're close to this limit, there will be we will be very, very close to v. So by definition, we will define it, the thickness of the boundary layer, as 99% of the external velocity. So it means we can then have, when we have a flow of air over a body, that is the relative representation of a body moving in still air, we will have then, due to the fact that the flow, that the air is viscous, we will have a boundary layer created above the body. And this boundary layer is the region where there's a gradient of speed, where the speed will evolve between the speed at the wall until the external speed. And so you already see that we have a lag of a flow rate that is between the wall and the end of the boundary layer thickness. And so this already will create some problems on the force that we'll measure. We can say also, as normally for our cases, the air has quite a low viscosity. The speeds and the size of the body are kind of definite dimensions. So for our cases of sports cars, racing cars, we will have quite high Reynolds numbers. It means the boundary layers will be quite thin. So a very thin boundary layer will be on top of the on the wall of the cars. So if we want to represent this with an example of a wing, we will have actually two areas. We have the area where the flow is influenced by the viscosity of the flow. So we have here represented the thin boundary layer between the wall of the body of this profile and the external flow. So inside we will have this gradients of speeds between the speed at the wall and the external speed. So in every point we will have a thin boundary layer. And once we are out of the boundary layer, the speed has refound what it would be, not disturbed by the viscosity, but still disturbed by the presence of the body. So we have one zone that is the boundary layer, that will be here, and the second zone is outside this boundary layer, where we can almost consider that the viscosity is negligible. Yeah, you see it here. And so we will have then in those terms, when we take back the NAVIER-Stokes equations, we will have the inertial effects that were initially in balance between the pressure effects and the viscous effects. So outside the boundary layer, we can consider the fluid as inviscid and just look at the variation of inertia of the speeds of the air in function of pressure. And this, for those who might have already seen it, is what we call the Bernoulli equation. So if we hear the terms of volumetric forces are still represented, but we have decided to neglect them. So if you look only at the bold terms, you will see that the pressure plus half rho v squared is a constant. So at whatever point, you will see the balance between pressure and speed. And that means that if the speed increases, the pressure will decrease, and vice versa. So you can illustrate it here for a flow into a tube. If there is a variation of section, then you will have at some stage when the section is smaller, the conservation of mass will impose that with a smaller section the speed has to increase, and if the speed increases by the Bernoulli equation, the pressure will be reduced. That means if the pressure is lower than here, locally the wall will see a suction compared to the other part. So the forces will be created. As we said at the start, the two main generators of forces are the pressure and the viscous effects. Outside, let's say, globally, in the region where we can neglect the viscosity, the main effects will be pressure. And you see already the pressure is varying with velocity. So where we will manage to make the speed increase, we will manage to reduce the pressure and create suction. And this can be good, for instance, to pull the car down and to increase downforce. In the boundary layer zone, what is happening? We can see that obviously when we have a uniform flow that's attacking, in this case, a flat plate that is stationary compared to the flow. So the relative motion is a speed on a stationary flat plate. Then the more we progress on the flat plate, the more the boundary layer will increase size, because it will depend on the distance of the particles on the plate, and the boundary layer will increase, and little by little we will lose more and more flow rate. So the viscous effect will be more severe towards the end of a body than at the start of it. And also, as we, in the mathematical approach, in our thinking of what is happening, as the boundary layer and the viscosity is very reduced for the air, so the Reynolds number is high, it means that the variations in x will be small. The trend will be that the evolution of the boundary layer will be small in the x direction, where the flow goes over a plate, for instance, but the big variations will be that as the boundary layer is very thin, it means over a very small distance we will have to vary between zero speed to the external speed, and so the variations, the d over dy's, the variation in the height in this case, in the y direction, will be much, much bigger than the variation in the x direction. So we have in the how we treat the equations, we will be able to neglect the terms of boundary layer will always be small compared to the dimensions of the body, that's written here, and the variations in Y will be much bigger than the variation in X for the boundary layer. This brings us to approach the flow separation. What is happening is you can imagine that when the air is flowing above a wall, in this case it's a curved wall, so we're also creating then, due to the curvature of the wall, we are creating a pressure gradient. On the flat plate, as there's no disturbance, no variation of curvature, it means the pressure over the flat plate will not change, so the boundary layer sees a kind of constant pressure. But if we start to have a wall that's curved, then in the first part of the curvature is in one direction until the maximum of this wall, we will have a kind of negative pressure gradient. In this case, the pressure will go lower and lower. And as soon as we have reached the top and we go further downstream, then the curvature of the wall is such that the pressure gradient is positive. It means the pressure is increasing more and more when you go downstream. You could imagine as a kind of an image, an analogy is like if as a cyclist you would see a kind of street that's going with more and more pendency. So here the pressure getting higher and higher, the boundary layer will have more and more difficulty to counter it, and in the regions where we have a positive gradient, there we have a risk that when the boundary layer is too weak, you will see that there starts to be return flow and we will have flow separation. So the important things to remember from this is as long as the pressure gradient is negative, so dP over dx is negative, then usually there is no problem at all for the boundary layer. That can be, for example, when you have a tube that has a section that is decreasing. When you have a section that is decreasing, it means the conservation of mass will get you that the speed is increasing, so the pressure is going down. There you have never problems. So in convergence, in subsonic, you never have problems of boundary layer separation. But as soon as you start to create divergence, so a tube that's expanding, expansions of tubes or expansions of walls, then you see that, again, the conservation of mass makes that the speed is getting down. And then you will have the pressure that is increasing again, and you have always the risk that you separate on an expanding wall. So this is an example of what can happen. And every time on the body, we will create curvatures that are creating positive pressure gradients, then we have a risk of flow separation. For instance, a roof of a car, the first part of the roof is okay because it's increasing, and once we're going downwards to the rear of the car, we will have risk of flow separation. Some examples of flow separation, the easy one is sharp edges, then the flow has no chance at all to be able to go around the sharp edge. So there we have imposed location of the separation, and we will have suction behind, overpressure in front. And if you look from Mucho, the different cars with different back of the car angle, when the angle is not so steep, the flow will remain attached because the pressure gradient in the curvature of the wall will be such that it's not enough to separate the flow. And then you don't need, for instance, for the cars that have a shallow angle, you don't need a wiper in case of rain. But when you start to increase the angle of the back of the car, there comes a moment where the flow separates and it's completely low suction, so no air is flowing around the glass and the screen, and so you need wipers in this case. So it is really separation depending on the pressure gradient. Same thing also for side vortices. When you look a car, a sketch of a car, you see the roof. The roof is going down, so the curvature is creating more suction here than here. And also on the side, as there's little wall curvature, the pressure will be at low variation. So you will find out that the pressure locally here is lower than the pressure on the side, and the flow will then roll over depending if this rear pillar is very sharp. You can have a structured vortex, but depending on the sharpness and the pressure gradient between here and on top of the roof, you can have structured or unstructured vortices. So coming back to the Navier-Stokes equations, now that we've introduced a bit the boundary layer and what's happening when the boundary layer has problems to resist to pressure gradients, what is the use of what we've seen on racing cars? So I come back, inertia effects are in balance with pressure effects and viscous effects. And we will see for racing cars, and you will see it also in the further courses with the CFD approach, the loads on racing cars are mainly coming from the pressure effects. So we will always try for racing cars to create suction under the car, suction under the front wing or a front splitter, or under a diffuser, under the floor, under a rear wing, to create suction to pull the car towards downwards, and this creates the downforce of the car. So it looks like the viscosity would have no effect, but actually its effect is we will not consider directly the viscous forces, but we will see that the pressure effects are very strongly influenced by the viscous effects. As we saw, when there's a positive pressure gradient, then there's a risk that the flow separates, and we will see an example just after to show you what it means. So we have to remember, in racing cars, most of the efforts, the forces are linked to pressure effects, and we will create curvatures to create suction. But the viscosity is always there, always the risk of flow separation, and so the viscosity will strongly affect those forces due to the pressure variations. To illustrate this, the best example is the flow around a cylinder or a sphere, and the drag is coming from it. So as an introduction, you can see that, maybe you know this, the drag of a cylinder or a sphere is quite high when the flow is laminar at low Reynolds number. Then it goes very low in a transition phase, and then when the flow gets turbulent, then at higher Reynolds number, then it tends to go slightly up again, but never reaches again the values of the low Reynolds number. Why is this due? It is because the drag of a cylinder is mainly coming again, like for example of racing cars, from pressure effects. So if you look the pressure distribution on a cylinder, if you describe it by the angle phi going around the car, so 0 is the leading edge, 90 degrees is the top, 180 degrees is the kind of trailing edge, 270 is the bottom, and you can reclose the cylinder. Then you get stagnation pressure, so the highest pressure at the leading edge, so Cp, the pressure coefficient will be 1 highest at the stagnation point at phi equals 0. Then the flow due to curvature going around the sphere will accelerate and will reach a minimum of suction at where we have the maximum y of the body before we will change of direction of curvature, and then the pressure will re-increase. So given curvature from 0 to 90, it is a decreasing pressure. Even if it's positive at the start, it's still decreasing all the time. And then once we pass the maximum y, the curvature is such that the pressure will recompress, re-rise, coming back to the trailing edge where we'll reach 1 again. And this is the theory where there would be no viscosity. So this you see in dotted line, and we call it like if the Reynolds number would be infinite. But unfortunately, and there's viscosity, so as soon as there is a positive pressure gradient, the flow will separate, or sorry, the boundary layer will suffer, and if the pressure gradient is too strong, the flow will separate. So in real life, when we are at low Reynolds number, what is happening is that the boundary layer, so we said that the Reynolds number is small, so the viscous effects are very strong, so the boundary layer will resist less to positive pressure gradients, and we will have quite an early separation. So we will have the front face that is completely at positive pressure, and the back face is very negative pressure. So it means the loads on the sphere or on the cylinder are all linked to pressure. Positive, we're pushing the body rearwards and pulling it rearwards at the back, but it's influenced by the separation due to the viscous flow. When we increase the Reynolds number, the boundary layer will resist a bit more, the flow separation will be a bit further, and so we reduce the zone where we are having suction behind the body, so we're reducing the zone where we're pulling the sphere rearwards, and it means a reduction of drag. So you see that's the explanation of this graph, and so it explains how the pressure effects are creating the drag, but as you saw, they are completely influenced by the state of the viscosity and so the Reynolds number. And this illustrates the racing cars are working exactly like this. You have cockpits, you have open wheels in the Formula 1, for instance. So it is regions where the flow will have difficulties to reclose behind. So there's risk of separation, and so risk of suction behind and creating a lot of drag. Yeah, the boundary layer states there's some kind of definitions. When at the start of a profile and at low Reynolds number, you will have a laminar flow, a transition, and then the flow gets to turbulent. And some experimental results, if once you want to calculate the drag, the friction coefficient of a plate, for instance, these are the Nicoretze, for instance, graphs, where you see that in laminar flow, the drag of a plate, the friction is lower and decreasing obviously with the Reynolds number. When you move to turbulent, you have higher friction, and there as well, when you increase the Reynolds number, it's decreasing. But as we said, we will kind of neglect a bit the viscous direct effects, and we will neglect a bit the friction due to viscosity on the bodies. And just also the quality of if you build cars, the quality of your cars, there will still be a small effect of this viscosity. So it's always important that your rugosities, your screws, the quality of your surfaces need to be well made enough, so that the disturbances are small compared to the boundary layer thickness. If they start to be big, then you will create vortices, you will create losses, and you will increase normally your drag. So this was a part of the introduction of how we create pressure variations and the impact on the boundary layer. The second part will be a direct application on airfoil theory. As you know, most of the racing cars create their downforce a lot through ground effect with diffusers, but the other big creation of downforce are the wings in opposite kind of functioning as airplanes. We just reverse the curvature, and we create downforce through a front wing and a rear wing of one or more elements. And the function of it, if you look on the right hand side, a profile that's completely symmetrical without any incidence in a symmetrical flow, as the flow is exactly the same on top and on the bottom, the flow will see some variation of curvature, so there will be variation of pressure on the profile, but they will be exactly the same. If there's suction in this variation of curvature on top wall, the suction will be exactly the same on the bottom wall, so a symmetrical profile will see no downforce, just a bit of drag. But as soon as you put this symmetrical profile at incidence, then directly you will see, if you do, for instance, flow visualization in with air with tufts, you will see that as soon as you change the incidence, there's a vortex emitted in the flow. And so if there's a vortex emitted in the flow, by conservation there must have been also a circulation around the profile. What means circulation means that there's different, if you combine a circulation with uniform flow, you will see that in one side of the profile the flow will go faster than on the other side. And if we say go faster, means that the pressure is lower, and if the pressure is lower than the other side, we will create forces in the direction of the lower pressure. And this is what we will try to do for profiles. So if we look at a profile, a given profile with camber, we can always describe this profile as the sum of a thick profile and a camber line. The thick profile will be, if we have the thick profile at zero incidence, it will be the part that creates no downforce, but it will create some variation of curvature, some variations of pressure. It is the clothing we put on top of the profile. And the camber line is what will create the real asymmetry, and so it will be the part of creating the downforce. The design parameters, I will show you after, a little tool that can to illustrate the different parameters that act on the wing. We can describe a profile by its chord length, by its thickness. If we look the symmetrical profile, that is a clothing of this profile, you can have a leading edge radius, you can have the position of the maximum thickness, you can have a trailing edge angle, and the same for the camber line. You can have a leading edge angle of the camber line, a trailing edge angle, and a maximum camber. So those are the parameters you could use to describe a profile. And I can show you a little tool that can be used for calculating and illustrating this. I will do ask. I will go to the program OptiProf, where I show you the same thing. So this is a program where the profile is described in the way that I just mentioned. So here we have selected just one profile, a main plane that has a given camber line and a given profile. And you see the first parameters are describing the camber line. So for instance, if I increase the maximum camber, you see at the bottom here, you see the camber that is increasing, and I can reduce the camber, and at the same time you see how the effect is on the profile shape. You can work on displacing the maximum, where the maximum camber is, the position. You can play with the angles of the leading edge and the camber of the trailing edge, and automatically the profile changes. You can play also with the parameters describing the thickness, so you can increase the thickness. You see the profile changing and the thickness profile changing. You can again change where is the maximum thickness. You can play with the trailing edge angle and the leading edge radius. And then the main parameters, you can play on incidences, you can play on chords, and the position of the wing. And this is then a calculation with panel code. It's a 3D calculation, so you can define how wide the wing is, you can define an end plate, and you can define the start of the calculation, and I will put number 2 because the baseline exists, and we can calculate and directly see the results. We get the downforce coefficient, the drag coefficient, and above all, what's of interest for us is the pressure distribution. So in this case, I've done just one calculation number 2, and we see that on this profile that I've defined, I have a given CP distribution. So you see I have much more suction on the bottom line, and on the bottom line of the profile than on the top line. So it means the area between the CP lines is representing the downforce I'm creating. So this is my baseline, and now let's see, I want to create, for instance, more downforce, and my first idea is I am increasing my camber line, so my maximum camber. I don't change anything else. I will tell it, okay, it's the third calculation, and so we will see directly calculation, what's the effect of increasing the camber. The calculation is done, I look at the results table, and I look at the pressures. So my baseline was calculation 2, and I've increased the camber by 3. So what did I do? You see my profile is with camber increase, my downforce coefficient has increased, and by what? By what mean is due to the increased camber, the flow went even faster on the bottom surface, so the pressure went even lower, and hence I've created more downforce. So this is an illustration how the wings work, and we can, with this tool in general, we can then go further and go to, we'll see it just after, we can go to multi-elements. So I hope I'm back at the same page. Yeah. So what's happening with this wing is a bit like in airplane theory. If we look at the airplane, what's happening is when I start to have a profile that's not symmetrical and at incidence, due to the overspeed on one side compared to the others, I get suction, and when I get suction, I also get at some stage recompression. And as we said, the main pressure effects created on the profile, for instance here, so I create really, in this case, lift on this profile. The pressure effects are influenced strongly by the viscous effects. How will it be influenced on the profile is if I put the profile too much in incidence, or if I create too much curvature, then the recompression will be at some stage too strong for the boundary layer to stay attached. And then I will have separation, and it's a stall of a wing. So what do the planes do? When they're taking off, when the speed is low and the mass of the plane is still very high, so to create a force, the downforce coefficient, so as the speed is low, we need then to increase the downforce coefficient. And the downforce coefficient, or in case for the plane, a lift coefficient, as the main plane cannot be curved more, we will create curvature and chord by creating a flap opening and a leading edge slot, so that the flow passing through the slot is helping the boundary layer to stay attached. And in the same way, we will have the same phenomena for our racing car wings, where we will have a main plane, and when the rule allows to have multi-elements, we will initially start to load more and more the main plane, because drag-wise it's always an advantage to have only less elements. But if we want more downforce and we arrive at the limit of the curvature of the main plane, and the flow starts to separate because the recompression is too big, then we will introduce a slot gap, and the complete curvature of the wing stays the one made through the two elements, but the additional energy from the top air will help the flow to stay attached, and we will hence be able to create to go to a higher level of downforce by increasing curvature. And the same philosophy can be increased and increased, and you can start to increase the curvature by rotating more the flap, curving more the main plane. There again, there will be a limit of separation, and then you can put a third element if the rules allow it, or a fourth element. And there have been times in F1 in the early 90s that we had until kind of 12 profiles on the rear wing end plates, because it was authorized to have that many, and we could create downforce by this multi-element assembly. One information about the real life. So obviously the wings have finite span, like on an airplane. So what happens if when we have a strong difference of pressure between one side compared to the other, then the air will want to limit this difference of pressure. So at the wingtip, you will have a kind of rotation of the air that is reducing at the end the downforce or the lift for an airplane, but the downforce of our cars, because the higher pressures will try to fill in to the low suction. And this is the three-dimensional effects. You see it can be very, very big effects because, as you see on this picture, the air force needed to lift even a small airplane puts a lot of rotation in the air, so it means there are huge variation of pressure between top and bottom surfaces that put the air in motion. And this is then what will create after the induced drag. One thing that's used on racing cars, I took kind of some older pictures because the current F1s are now full of louvers and discontinuities everywhere. But to try to help, a bit like winglets on airplanes, to try to reduce this flow that goes from the top to the bottom and circulates, that is illustrated by the humid air on this F1. The end plates are used for this, above all on the rear side, and this limits somehow a bit the variation of pressure between top and bottom and keeps the downforce a bit higher. One word on what is a very cheap device but very, very common in motorsport is the trailing edge gurney. The trailing edge gurney has an advantage. It has a fixed position of separation. The little suction it creates behind helps the flow to stay attached. It acts like a local, very high variation of curvature, and it is a bit like having a wing that's more inclined or a wing that is more curved, and it creates definitely more suction on the bottom and even an overpressure on the top, so increasing quite a bit the downforce. It has an advantage that it's quite having the same kind of separation whatever the speed, so the wing behavior will be more stable between slow speed corners where the Reynolds number goes lower and where the wing will be more affected by viscous effects, to high speeds where the Reynolds number is higher and you have less influence by viscous effects. So at the end, the gurney is a good tool to stabilize the car and to give more downforce. And finally, a word on vortex generators. They're often used on splitters. It means the splitters, here's a picture for the Porsche in the WEC World Endurance. Behind the main plane, the flaps are quite steep, and so sometimes it helps, like on airplanes as well in front of the flaps, it helps to create some disturbances to give energy to the flow and help it to stay better attached on very steep surfaces where the pressure gradients are high, so where the boundary layer is at risk, and so there the little vortex generators will help to keep the flow attached, and so you can use your geometry to create more downforce. So this ends my introduction to the fundamentals of aerodynamics that will be of use for you to understand what is needed for racing car designs. So don't hesitate. If you have questions, please ask them now.
René, thank you very much for this great introduction. And again, I was really impressed by how you explained complex things in a very, very simple and easy to follow language. And we already have some questions. In the case you have more questions, guys, you need to ask them now. And the first question is by Tom. And Tom wants to know if F1 teams simulate with compressible or incompressible air when doing CFD.
So most of our tools are taking into account compressibility, but the effects will be very small in most of the cases. And so yeah, the effects are included in the tool, but usually it's not a kind of main effect on the results.
All right, thank you very much. The next question is by Gabriel, and is there He wants to know if it's, sorry, he wants to know if it's possible to receive the presentation slides after the webinar. This is something I need to discuss with Renee and also with our department, and we will decide it, and if it's possible, we will send it to you by email. All right. The next question is by Animesh. He wants to know how the drag is created due to the flow, and if you can maybe explain it again.
So the drag is creating, it has two main factors. One is, we said, we tend to neglect it in motorsport, is the direct viscous effects. So as the flow is viscous, and the friction of the air on top of a wall will create friction drag. So it is tangential to the surface, so pulling the surface to the back, and this is called the viscous drag. But on racing cars, the biggest contribution of drag are two coming from the pressure. So there are regions, like we saw on the sphere, there are many regions where there is an overpressure on the front face, so pushing the bodies rearwards, and due to the curvature there will be suctions on the back face, so pulling the surfaces rearwards. So those are really contributing to pressure drag. And the other term that's very big is what we just saw on the last picture about the airplane vortices, due to the tip vortex on wings, for instance, is racing cars, above all Formula Ones, they're creating a huge amount of downforce. You can imagine, I think, end of straight, to give you a figure, it is for cars that are around 700 kilograms, it's over 2.5 tons of aero downforce, end of straight, so it is huge effects. And the downforce comes from difference of pressures between one side to the other, and the fact that we're not totally sealed, the suction part is never completely sealed from the more higher pressure side. The vortices we create by the downforce due to this pressure difference is what we call induced drag, is those vortices you saw on this picture before, and this is also a big contribution to the drag of the cars. So you have induced drag due to the downforce is a big contribution, and pressure drag, that is due to the shape of the body. Coolers have also big differences of pressure between the front face and the back face. So the difference in pressure between front face and back faces are really creating drag by pressure difference.
All right, René, thank you very much. A lot of different persons like Gabriel and others ask about vortex generators. So could you maybe again quickly explain how vortex generators are working? And also they ask, where do you see the biggest potential to apply vortex generators on a Formula Student car?
So vortex generators are normally fitted in regions where already the curvature is such that the pressure raises again. So downwards curvature, so when it's the convexity in the direction of reclosing the shape, like the back of a profile or the back of a car, the roof of the car. So there, the vortex generators, by their shape that is slightly inclined compared to the flow, and the sharp edges are creating a little vortex. The vortex somehow gives a bit energy to the boundary layer, and this additional energy helps if it was critical, if the boundary layer was at the edge of separating, so at the edge of not resisting to the pressure gradient, then this little additional energy will help it to stay attached. So the fact is, so you have to look, ideally on your student car, you will try to design your body in such a way that the curvature of your walls are not too extreme, so that the flow doesn't separate on its own, because there's always a penalty of drag to pay for vortex generators. So in some cases, like we saw in the Porsche WEC car, the total benefit is, or say the total between the gains and the losses of drag are really in favor of the gains. You get big gains by creating more curvature. So on downforce generating elements, if it helps you to keep the flow attached and to create much more downforce, then it's worth the price of the little drag. But when you're making very, very kind of efficient low drag bodies, then it's better to pay attention and to spend time maybe with the CFD tools that you will see in the later webinars to try to optimize your curvatures and your pressure distribution so that your flow stays attached without needing vortex generators.
All right, thank you very much. And where do you think the application of vortex generators in Formula Students, where could it make sense?
But if you have surfaces that really need to reclose, like for instance if you have covers around your wheels, or if you have the trailing edge of your cockpit, if you have for whatever reasons to close it a bit too sharply, then you could put some little vortex generators sorry, at the start of the reclosing of the body, so that the vortices will help the boundary layer to stay attached. And then you have also less drag because you will have less wake of your car.
All right, thank you very much. Daniel wants to know if you can explain how the extra inertia of a turbulent boundary layer can produce more downforce than a laminar boundary layer.
It's a bit the same thing as these vortex generators. What's happening with turbulent boundary layers is that the disturbances, there's a multitude of little vorticity inside the boundary layer, and this gives it more energy, and due to the more energy, the boundary layer resists better to gradients, to pressure gradients, but at the same time, as there's more energy, there's more friction. That's why also there's more drag. So the laminar boundary layer is very good for low drag, but resists less to separation. And as an example, you could see when you open a water tap, if the water tap is a nice tube, you will often see when you don't open it too fast, it's a very nice water flow and you can see through it. But when you open it faster, so somehow you increase the Reynolds number, suddenly it starts to be very, very turbulent, and there's a lot of mixing of the flow that is turbulent. So it is more energy in the flow, but also more drag on the surface, more friction on the surface.
All right, there are some more questions, and I think at some point we can't accept any additional question, guys. I'm sorry, but you've asked so much, and let's try to answer as much as we can. Manish wants to know, what do you think, if it's better to use a barge board or a splitter at the side pod, keeping the wind wake in mind?
So it depends what you call splitters. So if you're speaking about inside, is it inside the side pods?
No, I think he's talking about, you know, if, as I understood him, like, well, if it's better for a Formula Student car to have barge boards or to have this kind of splitter with this below, you know, at the, where the monocoque, where the end of the nose cone is attached to the floor. Maybe Monish can specify his question a little bit more, and in the meantime we can ask some other questions.
Because yes, it is, sir. I think if it's about the flow separation inside the side pod.
It's about what? Flow separation, the side pod, or about the other thing, Monish?
Around the side pod. Is it around the side pod, or is it internal flow or external flow?
Yeah, it's his writing. Maybe he explained it. He wrote yes, but I don't know what yes means in this context. So let's proceed with another question, and maybe he wrote it now. The side pod house of the radiator, the wind wake from the splitter inside the pod will affect the overall cooling of the system. Yes.
Yeah, so it's right. So you must always try, for side pods and cooling, you must always try to get the less disturbed flow into the side pod. So that's why sometimes there will be barge boards in front to displace kind of lower CPT, so it means flow that has been disturbed coming from the front, if there are vortices or losses from the front, to try to get them out of the way from the side pods. Or you can try with barge boards trying to deflect the flow so that only good flow is, let's say clean, in brackets, clean flow will enter the side pods, but it's sure for good flow functioning, it's important to get good flow into the side pods, and after to slow it down in a good way. Having splitters inside the side pod to separate flows inside the side pods, that usually doesn't work very well. Often it's better to design well your ducts, and according to your different pressure loss coefficients from your coolers, it's better than to have to add splitters, because it's always very difficult. They're always more lossy than only in very extreme cases they will work.
All right. Henrik wants to know if it is possible to apply machine learning for airfoil profile design with respect to the optimal ratio between downforce and drag.
So I think you can definitely put an optimizer on the system. I think more optimizer than machine learning, even if it's the techniques sometimes tend to go in the same way. What's important, where the importance of the LRM assist is fundamental, is defining the boundary conditions of your optimizer. So you have to tell the system what you're really looking for, because you can say, I want a given drag and more downforce, but you have to limit the drag, or you can accept to have more downforce, more drag, but at a given ratio. So and you have geometrical constraints that are often there in motorsport rules, so you must limit the rules, and very often as well your wings will have an influence on other parts of the car, so you will need to determine the conditions, the constraints that you want. But otherwise it's possible to let a system optimize, if you have enough calculation power, to come to a kind of an optimum for a given configuration. But you must always remember that as soon as you rechange your front wing or your nose or your chassis, the flow towards the rear wing is again different, so it is a continuous improvement.
All right, thanks. The next question by Francesco. Is there a way to determine the exact height of the boundary layer? Maybe I can jump in here. In the end of the day, it's just a question of definition, Francesco, and usually you have this criteria around 99.8% of the reference inlet velocity, and actually we will show in the workshop how to visualize the boundary layer using CFD, and if you want to do it in a wind tunnel, well, you need a PIV system or something else to, in the end, get the velocity profile in a plate. Next question is by Marco. He wants to know, can you make a kind of skirt effect with two lateral vortices in the underbody of the car? If it's possible, why does it physically work?
Let's say somehow there have been times in F1 where people were kind of using a bit the principle with, for instance, exhaust blowing. So the exhausts were blown on some surfaces that were creating a vortex, and they were sealing the side of the diffuser. So this you can try with some elements that the vortex himself will prevent the outer flow to try to reduce the suction, for instance, under the floor. So that has been a big help from the CFD in the recent years. It is, with the CFD you will be able to visualize, let's say, the consequence of the ideas you have of how creating some special walls, some special deviators, some special barge boards that will create vortices, and to make those vortices do what you would like is really a big advantage from the CFD. So in effect, in some conditions, when the rules allow it, you can try to make vortices that seal various areas of the car. Milad?
Oh, sorry, I was muted. Yes, I just wanted to say that was the last question. Thank you very much for being here with us. It was a great pleasure, and I think this is a great starting point also for the students. Also, thank you very much to all the participants. We will be back next week with our introduction to CFD. Yes, hope to see you next week. And yes, again, thank you very much, René. Have a nice evening.
Yeah, thanks. Goodbye.